Our first lesson in Chapter 6 is on discrete and continuous random variables. In this section, we'll look at applying the concept of discrete random variables to a variety of statistical settings, calculate and interpret the mean or expected value of a discrete random variable, and calculate and interpret the standard deviation and variance of discrete random variables. We'll also describe continuous random variables. A probability model describes the possible outcomes of a chance process and likelihood the outcomes will occur. A numerical variable that describes the outcomes of a chance process is called a random variable. The probability model for a random variable is its probability distribution. A random variable takes numerical values that describe the outcomes of some chance process. The probability distribution of a random variable gives its possible values and their probabilities. Example, consider tossing a fair coin 3 times. Define x to equal the number of heads obtained. Here are the possible outcomes. The probability of 0, number of heads, 0 heads, is 1 out of 8. 1 is 3 out of 8. 2 heads would be 3 out of 8, and 3 heads would be 1 out of 8. Here is the probability, value versus probability in a histogram. Remember that the probability can be listed as a fraction, a decimal, or a percentage when you're listing it on a histogram. There are 2 types of random variables, discrete and continuous. If we can find a way to list all possible outcomes for a discrete random variable and assign probabilities, we have a discrete random variable. A discrete random variable takes a fixed set of possible values with gaps between. The probability distribution of a discrete random variable x lists the values and their probabilities. It must satisfy 2 requirements for the probabilities. Every probability is a number between 0 and 1. The sum of the probabilities equals 1. And to find the probability of an event, you add the probabilities, the p-values, or probabilities of the particular values that make up the event. Example, show the probability distribution for x is legitimate. Make a histogram of the probability distribution. Describe what you see. APGAR scores of 7 or higher indicate a healthy baby. What is the probability that x is greater than or equal to 7? Here's our solution. All probabilities are between 0 and 1 and they add up to 1. So it's a legitimate probability distribution model. Here's a histogram. The score versus the probability as a decimal. The skewed left shape of the distribution suggests a randomly selected newborn will have an APGAR score at the high end of the scale. There's a small chance of getting a baby with a score of 5 or lower. And the final one is the probability of x greater than or equal to 7. We take a look at all these probabilities and add them together. 0.908, which is a 91% chance of randomly choosing a healthy baby. Here's another example. In 2010, there were 1,319 games played in the National Hockey League's regular season. Imagine selecting one of the games at random, then randomly selecting one of the 2 teams that played in the game. Define the random variable x to be the number of goals scored by a randomly selected team in the randomly selected game. The table below gives the probability distribution of x. Show the probability distribution is legitimate. All the probabilities, again, on this list are between 0 and 1, and they all add up to 1. So it's a legitimate probability model. Make a histogram of the probability. Here's the histogram of the goals versus the probability. We can see the histogram shows that it's skewed to the right, which means the majority of games are relatively low scoring. This is pretty unusual for a team to score 6 or more goals, given the results of the histogram. So what is the probability that a team selected has at least 6 for the randomly selected game for the number of goals? So probability x greater than or equal to 6. We take probability of 6, 7, 8, 9, add them together, which is 0.061, which would be a 6.1% chance. Here's another example. Another wager players can make in a roulette is called a corner bet. To make a bet, a player places his chips on the intersection of 4 numbered corners or squares on the roulette table. If one of these numbers come up on the wheel and the player bet $1, the player gets his $1 back plus 8 more. Otherwise, the casino gets the original $1. If x equals net gain from a single $1 corner bet, the possible outcomes are x equals -1 or x equals 8. Here's the probability distribution. Either we lose $1 or we gain 8. What is the player's average gain? In the long run, the player loses $1 in 34 of every 38 games and gains $8 in 4 of every 38 games. So imagine a hypothetical 38 bets. The player's average gain would be, we add all of these together and divide by 38. We'd have -1 times 34 out of 38 plus 8 times 4 out of 38, and we get -0.05. It would be a -0.05 cents per bet. And in other words, the casino keeps 5 cents of every $1 bet in roulette. When analyzing discrete random variables, we follow the same strategy we used with quantitative data. Describe the shape, center, and spread, and identify any outliers. The mean is an average of the possible outcomes, with each outcome weighed by its probability. So to find the mean or expected value, multiply each possible value by the probability, then add all the products. Compute the mean of the random variable x and interpret it in context. So we take each value times the probability and add them together. Our total, 8.128. So the mean APGAR score of a randomly selected newborn is 8.128. This is the long-term average APGAR score of many randomly chosen babies. Note, the expected value does not need to be a possible value of x or an integer. It's a long-term average over many repetitions. In the National Hockey League example earlier, we defined the random variable x to be the number of goals scored by a randomly selected team in a randomly selected game. Compute the mean of the random variable x and interpret this in context. So we take each of the goals times the probabilities and add them together. So the mean number of goals was 2.851. So if we were to repeat the random selecting process over and over again, the mean number of goals is 2.851 in the long run. Standard deviation. We use this for a measure of spread. Definition of variance is similar to variance for a set of quantitative data. To find the variance, we take the x minus the mean squared times the probability for each one and add them together. Remember, standard deviation is the square root of variance. Compute the standard deviation. Value minus the mean that we calculated earlier was 8.128 squared times the probability, plus value minus the mean squared times probability, and so on. We get 2.066 for the variance. Square root it, 1.437 for the standard deviation. So on average, randomly selected baby score will differ from the mean 8.128 by about 1.4 units. Here's another example. Earlier we calculated the mean for the National Hockey League goals to be 2.851. Now we're going to compute and interpret the standard deviation. Take each value minus the mean squared times probability. Do that for each one. Value minus the mean squared times the probability. Add all those values together. We get the variance. Take the square root of the variance, 2.66, we get 1.63. So on average, a randomly selected team's number of goals and a randomly selected game will differ from the mean by about 1.63 goals. Situations that involve measuring something often result in a continuous random variable. A continuous random variable x takes on all values in an interval of numbers. The probability distribution is described by a density curve. The probability of any event is the area under the density curve and above the values of x that make up the event. The probability model of a discrete random variable assigns a probability between 0 and 1 to each possible value of x. A continuous random variable y has infinitely many possible values. All continuous probability models assign probability 0 to every individual outcome. Only intervals of values have positive probability. Many calculators and statistical software packages can generate random numbers from a normal distribution. For example, on the TI-84, pressing rand norm 01 over and over will generate a distribution that can be represented by the standard normal curve. The z equals the result when random norm 01 is pressed. The probability z is between -1 and 1 is about 0.68. This is shown in the figure where the area under the curve between -1 and 1 is about 0.68. Define y as the height of a randomly chosen young woman. Y is a continuous random variable whose probability distribution is n 64, 2.7. What is the probability that a randomly chosen young woman has height between 68 and 70 inches? Mean 64, standard deviation 2.7. What's the probability? So here's how it would look. Probability y is between 68 and 70. Find the z-scores. 68 minus 64 divided by 2.7. Again, review that this is the value minus the mean divided by standard deviation. So we're finding the probability z is between 1.48 and 2.22. Find the values from our table or graphing calculator. Remember the area is figured out to the left, so we want the 70 minus this area right here, which is the 68, which is the 2.22 and 1.48. Subtract 0.0562. So about 5.6% chance a randomly chosen young woman has a height between 68 and 70 inches. In our next example, we're looking at weights of 3-year-old females. What's the probability a randomly selected 3-year-old female weighs at least 30 pounds? Our mean is 30.7, standard deviation 3.6. We standardize the weight and use table A to find the shaded area. So our z-score is negative 0.19. Finding the probability z is less than negative 0.19, which if we look that up in table A is 0.4247. So the probability z is greater than or equal to that would be 1 minus that, which is 0.5753. There is a 57.53 or about a 58% chance randomly selected 3-year-old female will weigh at least 30 pounds. In our next lesson, we'll look at linear transformations, combining random variables, and combining normal random variables.